Next, let's see how the corresponding on-disk data structure, the different parts of the on-disk structures get touched when a specific file system related operation is performed, specifically creating a new file and writing to a new file, okay? So over here, in this slide, in the next couple of slides, we're going to use this example to kind of illustrate this different file system related operations. In this case, the first example is how the different parts of on-disk data structures gets touched when a user tries to create a new data file. In this case, it tries to create a data file which is called bar under the directory foo, under the root directory. Okay, it tries to create this file, and this is a new file. Okay, and over here, this table, it shows a table kind of like on disk data structure and how the disk-based file system image gets organized, gets laid out. Okay, and the first, it gets divided into three parts. Three sets. The left set, the left part, is the bitmap part. Okay, it has a data bitmap and inode bitmap. Whenever you want to allocate a new bitmap, or whenever you want to allocate a new data region for storing a new file, you need to look into the data bitmap. And whenever you want to create the new file, you need to first create the new inode data structure corresponding with that file. So you need to look into the inode bitmap first. Okay, so this is the first view. So the second three columns, the center part, the root inode, foo inode, and var inode, so these are the inode table. That stores all the inode data structures, and each and every one of them points to a unique data file or a unique on-disk directory file, okay? So these are the central part, and the rightmost part are the two columns, each corresponding with a particular directory or particular data, okay? In this case, the root data is corresponding with this root directory, and the foo data is corresponding with the foo directory, okay? So given its current format, the bar data file hasn't existed, okay? So we need to create it. In order to create this, you need to first perform a path traversal. It traverses through the root directory in order to identify and tries to locate to the correct subdirectory, which is foo, right? So in order to do so, you need to first refer to this root inode data structure. So that is why you have a first read operation over here that touches this root inode directory so that you get the basic information about how many subdirectories under the root directory and where exactly the foo directory is located, okay? And then follows by a second read because you need to read in the root directory, which is stored as a data region. So the rightmost part is reserved for the data region, which is used to store for files and directories. So the second read touches a root directory, okay? And then followed by another round of read operations because you have already identified and located the foo subdirectory. So the next set of read operation is to basically look into the foo directory and see how this bar data should be created. Okay, so followed by this read because it touches this foo inode. Okay, we're over here right now. It touches this foo inode, and then under foo inode, you know about where exactly this foo directory gets stored on disk within the data region, and then followed by the second read to read into the data region. where the full directory gets stored, okay? And you further check the full inode to see if we have the right permission to create the new data file, which is called bar, okay? And you get the answer that the bar data doesn't exist, okay? So this is answer. The bar data doesn't exist, so what you need to do next is you need to, allocate new inode, which is associated with this newly created bar data, and then go ahead and create the new bar data fields within the data region, the file fields within the data region, okay? So the next step is to allocate new inode. So in order to allocate new inode, you need to first refer to the inode associated bitmap data structure. So that is why it comes with a bundle of read and write operations, because you need to first read in the inode bitmap data structure into the memory, and then you perform an update operation to try to identify and locate an available bit, and that bit is associated with a particular inode data structure within the inode table, okay? You try to locate that. And the next operation followed by that is to allocate a new bar inode, which is over here, okay? And read it out and update it, okay? Because you need to populate, the next step is to populate this inode data structure. And the last step is to add the bar field, add the bar data file under the subdirectory /foo, okay? So it's followed by two write operations. The first write operation is you write into this foo inode because you need to basically update its parent directory, which is foo. And then you need to create the file under the foo directory. And then you have to really go into that data region, which is located over here, followed by another write operations, okay? And then you go ahead and create a bar data over here, but which hasn't been shown over here, and it will be shown in the next couple of slides, okay? As you can see, so the whole process of creating a new data file involves so many random read and write, small read and write operations, okay? So that implies in order to optimize the file system related operations, you need to really be careful. You need to make judicious decisions with regard to where exactly you want to place all this data. And the ultimate objective, especially in the context of using hard disk drive as the secondary persistent storage, is you want to always maximize the chances of sequential large read and write operations, because hard disk drive is really good at sustaining sequential large IOs, but instead of sustaining random small IOs, it sucks at supporting random IO operations, workloads, okay? So keep that in mind. So let's take a look at the next set of operation. So the next operation is, let's assume right now, this bar data has already been created, okay? So this bar file under subdirectory foo under the root file, or the root directory, has already been created and populated. And the next operation is the user want to write something new into this newly created file data, okay? But let's assume this data block reserved by the bar inode has already been full. How to make sure that the block is full is by basically reading in the bar inode by performing a disk read over here, and it checks, oh, all the data blocks that are covered by this inode are full. So you need to allocate new data blocks. So how to allocate new data block is you need to first refer to the data bitmap located over here. So that comes to the next set of read and write operations. Again, similar to how you create a new inode data structure. You need to first read the data bitmap into the memory by issuing a read operations and then followed by a write operations, okay? To basically update the bitmap to identify a free bit associated with a particular available free data block on disk within the data region. Over here somewhere, okay? And then you need to update this bar inode because you need to populate this internal content information within bar inode to add in more data block pointer to basically enlarge this address array to incorporate one more data field, one more data block by basically issuing an update write operation against this bar inode, okay? So you add a pointer that points to this newly allocated on disk block, okay? And then followed by the last write operation, which is you want to write something into this data block that you just allocated, you go ahead right to the data region. So this is the last write operation, okay? So you can see the write operation is relatively easier compared to the create operation. So the main takeaway is the create kind of operation is more metadata heavy operation as compared to the write operation, because write operation, it just involves like at most 2 reads. The first read, the second read, and at most 3 writes. The first write, second write, and third write, okay? But again, if you want to just simply write something to a new file, something to an already opened up file, it involves multiple read and write, small read and write, random IO operations against the on-disk data, okay, as part of this file system image. And over here, the first 2 fields are corresponding with the directory entries, whereas the third field is some real plain data file, okay, which is the bar data. So next, let's talk about how different data layout strategy would impact this file system performance, assuming the file system is within hard disk drive, mechanical hard disk drive. So recall that when talking about the memory management topic, we've studied these 2 different kind of locality properties. The first one is sequential locality, spatial locality, and the second one is temporal locality. So the definition, so how to understand spatial locality is the next reference is located within the parameter of the previous reference, is near the previous reference. Okay, so this is spatial locality. And temporal locality is also easy to understand. Temporal locality means the future references are basically simply repeating what has been observed, what has been referenced in the near history. Okay, so it just simply repeat the old access pattern just like this. Okay, and this is a timeline. The second half of the time, all the references are basically repeating what has been done, what has been performed during the first half of the time. So this is temporal locality. Okay, so in the context of a disk-based file system, the first question to ask here is, what types of locality are used for a cache? Well, the answer is possibly for both spatial and temporal locality, they benefit a cache design. But if you take a look at the same question but under a different context, what types of locality are useful for a hard disk drive or mechanical disk? Well, it's probably spatial locality. Why? Right? Why is that? It's because the disk simply sucks in sustaining random I/O workloads, but it could provide reasonably good sequential performance because it's good at it features like relatively high sequential bandwidth. So that's all the reason. Okay. So with that in mind, let's see whether the order of accessing the on-disk data would impact the performance. Okay. So in this slide, we have two workload A and workload B. So workload A, as time goes by, the disk access pattern is basically you go ahead and access the monotonically increasing address. Okay, so the Y dimension is the address. As you can see, as time goes by, you increase the address and go ahead and access the next address adjacent to it, an X address, basically this diagonal pattern. Okay, so this is a workload A. In contrast, workload B, it goes the opposite direction, the reverse direction. So the next reference, the next disk access is following decreased address. So the next memory, so the next disk access is targeting its previous, its left address field. Okay, starting from the height address goes monotonically decreasing address. So which workload is good for file system and which workload is bad? Obviously, the first workload A, performs significantly faster compared to that of workload B. Why is that? It's because if you just simply follow this monotonically increasing address range, address sequence, you basically can just issue a large sequential read and write, right? Which is really good for a mechanical hard disk drive. But in contrast, for workload B, because the hard disk drive is not flexible in the sense that the rotating or the spinning direction of the surface, the platter, is only on a single direction. Okay, it's either clockwise or counterclockwise. It cannot be both. So given this, if you want to access a previous, like smaller address, you need to wait for this whole platter to rotate almost the whole circle before you reach the previous, the smaller address. So this way, for workload B, it will be extremely slow. It can be 100 times slower compared to the speed of workload, the performance of workload A. Okay, so that means the order does matter for the file system access if the file system is sitting on top of hard disk drive. So another interesting topic is how to choose the data layout, how to basically perform, how to choose the data placement strategy with regards to placing inode data and the data blocks, okay? Basically data placement policy. So the first example is some bad file layout example. So let's assume the inode is allocated within the first inode block somewhere over here. And the first inode is its corresponding file. It's a large file. It spans 4 different data blocks. And we have the first data block 0, the second one, data block 1, data block 2, and data block 3. It's scattered and spread across the whole range of this data region. Okay, this is obviously bad for a disk-based file system because in order to just get access to this single file, requires 4 small IOs, and these 4 IOs, each has a far distance against each other. Okay, so I have to access this one first, this one, and that one, and another one. Basically, it requires the disk arm and the surface to keep rotating, and you require the disk arm to be like spinning, moving back and forth. Okay, so which increase the performance overhead. A relatively better file layout is to try to honor this sequential I/O pattern, to try to preserve as much sequential I/O as possible. So in this example, instead of randomly spreading these 4 data blocks that belongs to this file, like in random place, like distant places within the data region, we just allocate these 4 together. So that if you just want to read out this file, you just need one sequential read, okay? But the only drawback over here for this relatively better file layout, even though it's significantly better than the previous one, it's still not ideal, because in order to perform sequential read, you need a separate small read. And this separate small read is to read this inode data information out from this inode table. And this inode table, so its corresponding inode data structure has a fair distance away from where its data blocks gets located. Okay, so this is still not perfect. So the best ever file layout that preserves the maximum level of sequential performance of a hard disk drive is to basically allocate inode data structure together with this data blocks, the data part, together in a sequential manner at the same location approximately. In this case, inode is allocated within the last inode block and adjacent to the 4 data blocks associated with this file. So in this case, hopefully, it just requires one single large sequential I/O. To first read the inode out into the memory, and then followed by the 4 data blocks that belongs to this file. So it maximizes the disk performance because it just require one sequential large read. Okay.